All right. Hey, everyone. So I'm here to give you some hints on 4.3.5 practice. Unit 4 is very difficult. You are not alone if you feel like this was a confusing unit. The stuff in this unit we usually spend in my honors chemistry class 2 months on, maybe even 3 months. So hopefully I'm going to try to explain it a little bit better than the textbook did and kind of parse some things out for you to hopefully make it a little bit more clear. But just do the best you can and don't worry, it's not you. This is a very confusing unit. So for question one, I gave you these answers just because there's no way to even tell the difference. The number of items in a mole, Avogadro's number, they're all the same thing. So you just have to figure out the other two. And you can look at 4.1.3 pages 2 and 3. And same thing for this, same part of the text. And then for C, 4.1.1, page 6. Right, and then this is where things start to get tricky. So it says, what is the molar mass of, hold on 1 second. I just need to get my periodic table here. Okay, so what is the molar mass of FeNO3 2? Okay, so first I just want to explain some things. So I'm going to do a little interlude here, and hopefully this will clarify a lot of what you read. Uh, so up until this point, this number at the bottom of each square on the periodic table, we've called it the average atomic mass. So it's the average mass of all of the isotopes of a given element. So for example, boron's average atomic mass is 10.81. Um, and that's the unit for average atomic mass is AMU. Okay, so for boron, there is 10.81 AMU. Oops, 10.81 AMU for every one atom. Okay, of boron. Okay, this line, so you could say 10.1 AMU per atom. So this line means per, or you could say for every. Okay, so 10.81 AMU for every one atom of boron. Or you could say for every one atom of boron, there's 10.81 AMU. Okay. The problem is, in the lab, we can't really deal with individual atoms. I can't just say, hey, get me 5 atoms of boron. Um, they're too small, and our scales in the lab don't measure in AMU. Our scales measure in grams. And AMU is really, really, really small unit of mass used to measure individual atoms, okay? Um, so this just doesn't really, it's not very helpful in the lab. So let's say I was doing a reaction that required that kind of followed this formula, 5B plus 2H2O, and it made something else. So for every 5 atoms of boron, I need 2 molecules of H2O, and I need to react them in that ratio. But unfortunately, I can't count out this ratio, okay? The scale just doesn't work for individual atoms and molecules, and I can't see them with my own eyes. So that conundrum is what led them to kind of come up with the concept of a mole. A mole is a number of atoms, 6.02 times 10 to the 23rd to be exact, grouped together. Okay, so just like there's 12 roses in a dozen roses, there's 6.02 times 10 to the 23rd atoms in a mole of atoms. Okay, so you might be wondering, like, why are they using that number? Why 6.02 times 10 to the 23rd? Like, why are they grouping them that? That's such a weird number. And the reason is that they realized that if they took an AMU, which is a very small unit of mass, and they scaled it way up, and they scaled it way, way, way up to a gram, they realized that there was 6.02 times 10 to the 23rd AMU in 1 gram. So we're kind of scaling this up by 6.02 times 10 to the 23rd, and instead of 10.81 AMU, it's 10.81 grams. Okay, but whatever we do to the top of a ratio, we also need to do to the bottom. So we also need to scale this up by 6.02 times 10 to the 23rd. And 6.02 times 10 to the 23rd atoms is 1 mole of atoms. Okay, this we can work with, right? I can measure out 10.81 grams of boron, okay, because my scale can do that. All right, so if I need a mole of boron, um, I need to measure out 10.81 grams, okay? And that mole of boron I know has 6.02 times 10 to the 23rd molecules in it, but I obviously can't see them, or 6.02 times 10 to the 23rd atoms in it, but obviously I can't see those atoms or count them out. But in my mind, I scaled an AMU up to a gram, and we scaled an atom up to a mole of atoms. And this is much more workable in the lab. So let's say I was doing this reaction, I would need 5 moles of boron and 2 moles of water, okay? So to get for 1 mole of boron, it would be 10.81 grams. For 5 moles of boron, I would just multiply this by 5, measure it out on the scale, and then I would have a sense of how much boron I had, okay? So the mole was kind of an invention that they realized provided that scale up that we need from an AMU, which is a mass that's way too small to measure, to a gram, which that's very easy for us to measure. So that's where the concept of a mole came from. And that's why a mole of atoms has this number of atoms in it, is because that's the number of AMU in a gram. Okay? So it's just kind of some background knowledge. So you can think of that number on the periodic table, the average atomic mass, you can think of it as the AMU in one atom, or you can think of it as the grams in a mole of atoms. Okay? So this, when we talk about just the AMU in one atom, we call this the atomic mass. Okay? So up until now, you've always called that number at the bottom the atomic mass, the AMU in one atom. But now, to be more practical in the lab, we scaled it up to have something called the molar mass. And the molar mass is not the AMU in one atom, it's the grams in a mole of atoms. Okay? So that's what they mean by molar mass. So to find the molar mass of zinc, it's right there, 65.39 grams per 1 mole, okay? Or if you want to know the molar mass of aluminum, it's 26.98 grams per mole, okay? So what you previously thought of as the AMU per atom, we can also think of as the grams per mole of atoms, okay? So that's just some background info on why they chose to have this many things in a mole. So when they ask for the molar mass, let's say they were just asking for Fe, okay, if it was just Fe, not with this other stuff, you would just look at Fe. The molar mass of Fe is 55.85 grams per mole, okay? To do FeNO3 you've got to add all these up, okay? So add up the mass of Fe. So we have 1 atom of Fe. And then this NO3, the N and the O are capitalized, so that's nitrogen and then 3 oxygens, but then there's a 2 on the outside of that. So it's essentially NO3 twice. So you can see there's 2 N atoms, and then there's 6 oxygen atoms, okay? So what you need to do is do 55.85 plus 2 times the molar mass of nitrogen, which is 14.01, plus 6 times the molar mass of oxygen, which is 16. Okay? And that's the grams in a mole of FeNO3 All right? Okay, B is where things get even more complicated. What is the number of moles in 27.6 grams of lithium? So to figure out the moles in this many grams, we need to use the molar mass. Okay? So if you look at lithium, it's 6.94 grams per mole. So I'm going to write that down. 6.94 grams per mole. Okay? And when I say it's the grams per mole, it's the grams per 1 mole. Okay? So it's 6.94 grams of lithium for every 1 mole of lithium. Okay? Or you could say for every 1 mole of lithium, that's 6.94 grams of lithium. Okay, these are equivalent. These are equivalent. For most fractions, you can't just flip them like that. You know, if I have the fraction 3 over 4, you can't just flip it and say, well, it's the same as 4 over 3, because those aren't the same. But this type of fraction, the top and bottom are equivalent, okay? They have different units and different numbers, but they're equal to the same thing. If I say I have a mole of lithium, that's the same thing as saying I have 6.94 grams of lithium. They're the same thing. So when the top and bottom are the same, you can flip the fraction because the fraction is equal to 1. It's like having 4 over 4. That equals 1, and you can flip it, and it's still equal to 1. Okay? All right. The other thing that they kind of snuck in to this unit that's a super big topic in chemistry that deserves its own unit almost is unit conversion. Okay, to do this problem, we need to convert from grams to moles. All right, and there's many ways of converting units that you've probably learned in the past. And the method that they introduced in this unit might have looked a little bit unfamiliar. Okay, so I'm just going to give you a crash course on that as well. So let's forget about moles for a second. Let's go to something much easier. Let's go to inches and feet. Okay, so if I said how many inches are in 17.5 feet, okay. If I said how many inches are in 17.5 feet, there's a lot of ways that you could do that conversion, right? Um, you probably know you have to do something with the number 12 because you know there's 12 inches in a foot. So you probably think, I either need to divide by 12 or multiply by 12, and you kind of go through that mental gymnastics. And probably you come to the conclusion, if you think about it long enough, that you need to multiply this by 12 in order to convert to inches. But there's a technique that's technically called dimensional analysis, but your book just calls it unit conversion. There's a technique you can use that makes this conversion a little more foolproof. And what you need to do is you need to take the number that they gave you in the problem, 17.5 feet, and just put it over 1, okay? And we're going to multiply it by a fraction that's equal to 1, where the top and bottom are equivalent. But we need to choose a fraction that will cancel out the feet and leave us with inches. So I'm not going to put any numbers in my fraction yet. Okay, I'm going to hold this spot. We know we need feet to cancel out, so I'm going to throw it under the bus. I'm going to put it on the bottom of the second fraction. And then whatever unit I'm going to try to get to, I'm going to put it on the top, like that. Okay? And then, now that I have the units in the right spot, I'm going to back up and think. Just ignore all this, and think. What numbers can I put in this fraction to make it equal to 1? This fraction has to equal 1. We need the top and bottom to be equivalent. So you probably know the number 12 goes somewhere, right? It's not 12 feet in 1 inch. It's 12 inches in 1 foot. Okay, so forget everything else. That fraction is equal to 1, okay, because the top and bottom are literally the same length. It's just different numbers and different units. So essentially what we did was we took our original length, we're multiplying it by 1, and we're going to get the same length. However, the units, because this unit's on the top and bottom, it's going to cancel out. The same way that if, I don't know, x is on top and bottom in an algebra class, you can cancel it out. And we're left with inches, which doesn't cancel out. All right, and that's what we want our answer to be in. So when you multiply fractions, you don't cross multiply when you multiply fractions. You might have forgotten that. You go straight across the top and straight across the bottom. Okay, so you do 17.5 times 12, and you get 210 inches. And then on the bottom, you do 1 times 1, and you get 1. And that's your answer. Okay? And notice how just by setting it up correctly, I did end up multiplying by 12, but I didn't have to go through that painful thought process of do I multiply by 12 or do I divide by 12 or what? Okay? Let's take another one. Let's say how many days are in 280,000 minutes. No, let's say this. No. How many days are in 743 hours? Okay. So you probably know you have to do something with the number 24 because you know that there's 24 hours in a day. But again, instead of having to go through that thought process of do I divide by 24, do I multiply by 24, we're going to use the same strategy we used up here. So put the number they give you, 743 hours over 1. We want hours to cancel out, so we're going to throw hours under the bus, okay? And we want to get to days, okay? Now I'm going to forget about this. What is the relationship between days and hours? What numbers do I need to put here to make this fraction equal 1, okay? It's not 24 days in 1 hour, it's 24 hours in 1 day. All right, and look at that, hours cancels out, and we're left with days. Multiply straight across the top. 743 times 1 day is 743 days. Multiply straight across the bottom. 1 times 24 is 24. And then you do top divided by bottom. So always simplify your fraction at the end, okay? So do 743 divided by 24, and you get 30.96 days, okay? So again, I didn't have to think it through. I didn't have to think, should I multiply or divide by 24? Because that process gets very painful, especially when we switch to units that we're not familiar with. These you could probably convert in your head, but I just want to give you easy examples. So when we use more difficult units like moles, you'll be familiar with this method of conversion, okay? So I don't want you to think the 1 is always on the bottom or the 1's always on the top. The 1 is just wherever it needs to be to make this equal to 1. This equal to 1. So for both of these, we started with the beginning measurement, we multiplied it by 1, and we got the same thing, just with a different number in a different unit. But these are the same length, okay? These are the same period of time. We just switched the unit using a method called dimensional analysis. So that's the method we're going to use to convert from grams to moles, all right? So just put the 27.6 grams over 1, put your time sign in your line, throw grams under the bus, and we want to end with moles, okay? And again, forget about this number. We need the top and bottom to be equivalent. So this is, we know that the relationship between grams and moles is the molar mass on the periodic table. So look at lithium on the periodic table. Its molar mass is 6.94. So you got to stop and think. Molar mass is the grams per mole. So 6.94 grams per 1 mole. Okay. So the 6.94 goes where the grams is, and the 1 goes where the moles is. So we're essentially using this form of the relationship. If we needed grams to, essentially, not this one, we're essentially using this form of the relationship. If we needed moles to cancel, we could use this one with moles on the bottom, but we need grams to cancel, so we're going to use this one, okay? So again, it's a flippable, it's a relationship. Because it's equal to 1, you can flip it however you need to in order for the units to go away that you need to go away. And then you multiply straight across the top. 27.6 times 1 mole is 27.6 moles. And then multiply across the bottom. 1 times 6.94 is 6.94. And you have 27.6. Always simplify it at the end. 27.6 divided by 6.94. And you get 3.976. So I'm going to round that to 3.98 moles. Okay. And then with these, you can always be sure, stop and be sure your answer makes sense, right? Just like for this, if it was 743 hours, you know, we know that that's like significantly more than 1 day, you know, so that kind of makes sense. Like about 31 days for that many hours makes sense, right? 17.5 feet having, you know, over 200 inches, it makes sense. So let's see if this makes sense. We have 27.6 grams. And we know that 1 mole is 6.94 grams, okay? So if 1 mole is 6.94 grams, that means this is more than a mole, right? And more than 2 moles. You know, around 3 or 4 moles sounds about right in terms of how many of this can fit in this. So 3.98 is a reasonable answer, okay? Question C, you can omit that. Question D, you're going to be doing the same thing we did in B at the beginning. First, this one's going to be 2 steps. So first, you're going to convert the grams of magnesium to moles of magnesium. So you'll do 48.6 grams over 1, throw grams under the bus, and get moles. Okay. So you're going to have to look at the molar mass of magnesium on the periodic table. Once you get your answer, then they want you to find the molarity. And the formula for molarity is the moles divided by the liters, okay? So once you get your moles, then divide it by 2 liters, and that'll give you the answer in molarity. All right. And I'm just going to omit these ones. So question 3A and 3B you can omit, and question 4A you can omit. Question B, number 1, you can look at 4.1.3, page 10, okay? The percent composition is basically just the part divided by the whole times 100, okay? So in this part, we have MgCl2, okay? So add up the molar mass of 1 Mg and 2 Cls, that's the whole. And then on the top, you just put the mass of just the magnesium. And then you multiply by 100, and that'll be the percent of this that's magnesium. And then for part 2, you do it for chlorine. So the part for chlorine will be the 2 chlorines added together over the mass of the whole thing again, okay? And then you'll multiply by 100. And your answers to both of those should add up to 100%, okay? So the answer to 1 and the answer to 2 should add up to 100%. For C, you can omit that one. For question 5A, look at 4.2.1, page 14. And for B, look at 4.2.3, page 2, 10, 14, and 20. Okay, for part C, I'm going to change the question a little bit. I want you to change it to this. Use the activity series of metals to predict whether the following single replacement reaction will occur. You don't have to tell me what the products are going to be. Just say, yes, this reaction will happen, or no, this reaction will not happen, and tell me why, okay? And if you look at 4.2.3, pages 16 and 17, they will tell you how to figure out if this reaction is going to happen or not. And that's all you got to tell me is yes, it will occur, or no, it won't occur, and explain why. And then for part D, use the solubility table to predict if a precipitate will form in double replacement reaction. A precipitate is when you mix two things that are dissolved in water. So this is a substance dissolved in water, this is a substance dissolved in water, and they react. Quite often they'll form a product that doesn't dissolve in water. And all of a sudden you'll see this kind of powdery stuff sink to the bottom. That's the precipitate. And the reason it's sinking to the bottom is because it made a new substance that doesn't dissolve in water. So what you need to do is go to 4.2.3, page 25, open the solubility table that's on there. There's a link to it. And that'll give you the rules for figuring out if a compound dissolves in water or not, okay? So if one of these does not dissolve in water, then a precipitate will form, okay? So just tell me if you find out that one of these doesn't dissolve in water, just explain how you figured that out and that's going to be the precipitate. If both of these dissolve in water, if they're both soluble, then no precipitate will form, okay? So it could be either of those scenarios. And then for part E, it's the same reaction, okay? But you need to specify the states, okay? So the thing that, if one of the products, if it dissolves in water, the state is going to be AQ, which means aqueous. So if it's soluble, according to the solubility table, it's going to be aqueous. So write AQ. If it's not soluble, that means it won't dissolve in water, and it'll be a solid that sinks to the bottom. It's the precipitate. So write S for solid, okay? In question 6A, look at 4.3.1, page 7. For 6B, look at 4.3.1, page 12. And for 6C, look at 4.3.1, page 13. For question 7A, look at 4.3.3, page 11. For B, look at 4.3.3, page 12. For part C, I'm changing the question a little bit. Complete the following combustion reaction. I'm not going to make you write it in two different ways, so cross off the second one. And you don't need to balance it. Just tell me what the products would be, but you don't need to balance it. So for that, look at 4.3.3, page 12. Okay? And then question 8, look at the 3 ways of drawing the hydrocarbon molecules, then write the molecular formulas. So to help with interpreting these drawings, look at 4.3.3, pages 3 through 7. Okay? So hopefully that has kind of helped elucidate some of the more confusing points of this unit. So If you're feeling overwhelmed by this unit, feel free to reach out for help. You're not alone, but hopefully by omitting some of the things and clarifying some of the things, hopefully that makes things a little bit more clear. All right, thanks a lot. Bye-bye.